Okay, so before we move on to today's lecture, I want to quickly recap what we covered in the last lecture. So in the last lecture, we started looking at the very basic four elements of reinforcement learning. And those four elements were: number one was the policy, number two was rewards, number three was values, and number four was model of the environment. So, what these four elements mean is that the policy is something which tells you the behavior of the agent. At every state of the agent needs to pick the best possible action, and this action selection is guided by the policy. So that's the policy. Then rewards are for every state which the agent encounters, the agent takes an action and immediately gets a reward from the environment. That's the second element. Values is something very different from rewards. Rewards is only considering about short-term desirability. But in value, we are considering long-term desirability of the state. We are not just individually evaluating single rewards, but we are adding all the rewards together till the end of the episode, and we are evaluating the return which the agent receives in the episode, not the reward. So that is the value. And last is the model, whether it is a model free or a model based environment. So many examples in this bootcamp, we are going to mostly look at a model free environment. Then what we looked at is we looked at specific type of state signals which satisfy a very unique property that to determine the dynamics of the system, you don't need to know anything other than the current state of the system. You don't need to know the history of the past. Whatever has happened in the past, we are going to say that, okay, we don't care what has happened in the past. We are only concerned about the present state of the agent. And all I need to know to predict the future is the present state. And this property of the state signal is called as the Markov property. And the state which satisfies that is called as a Markovian state or a Markov state. So in the remainder of the bootcamp, we are going to be only looking at processes which are Markovian in nature. So when I say that, I mean all the states or observations that we are going to encounter, they are going to satisfy the Markov property. That's going to be the implicit assumption in all the examples that I'll be discussing even today. So I won't reiterate again and again that this satisfies Markov property here. Towards the end of the last lecture, we saw how to work around with OpenAI Gymnasium and how to control a lunar lander to land on a surface. But we noticed that we are missing one key element there, which is the policy. That's the reason we took random actions for every state. The objective was to show you that reinforcement learning can be very practical also, and I wanted to give you a flavor of how to implement the agent environment interface in practice. So in today's lecture, we are going to focus on this part. So in particular, we are going to look at how to take actions that make sense instead of taking random actions for every state. And everything boils down to this. You can model a reinforcement learning system very nicely. You can tell me that I have modeled the agent environment interface. These are the states, these are the rewards which my agent is receiving, and these are the type of actions. But it won't be useful at all unless you tell the agent what actions to take at each state. And that is exactly what we are going to focus on today. So, whatever we are going to cover today comes under the field of classical RL. It is extremely important to understand all the modern reinforcement learning algorithms. And I would say This part is where all the major development has happened. Everything that has happened has built upon the classical reinforcement learning algorithms. So we are going to look at one important definition to start this lecture with, and that definition is called as the state value function. Right now, we have only discussed about values in an intuitive way, but we haven't really discussed about what is the meaning of value of a state. And I'm going to explain this with an example. Let's say you are at a specific state, and there are a bunch of actions possible in that state, but you take action A1, you land in state S1. You take action A2, you land in state S2. Similarly, you continue it till you take action AT and land in state ST, which is the end of the episode. The question that I'm asking is, what is the value of this state? And the way we formulate it mathematically is, we look at all the rewards which the agent receives. So from S to S1, the agent receives a reward of R1. From S1 to S2, the agent receives a reward of R2. And here in the last step, the agent receives a reward of RT. So the value of this state is going to be the summation of all those rewards, R1 plus R2 plus dot 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 RT. Let's say it comes out to be 30. So then you might ask me the question that, Rajat, this is fine, but what if in the next episode, this agent follows a completely different trajectory and you get a expected return of 50 or a return of 50. So these returns might vary for different trajectories or different episodes which the agent follows. So what we do is we take the mean of all this. In other words, we take the expected value of the return. Remember in the last lecture, we talked about returns, which is denoted by G of t. So essentially, how we calculate value is that we say that let's run the agent for, let's say, 10 episodes. We calculate the return for each episode. We add them up together and we divide by 10 to calculate the mean of all the returns. So this is exactly what the value function of a state is defined formally. It's defined by saying that the value function is the expected return which the agent receives starting in a state and following a specific policy thereafter. I never told you how I'm choosing these actions. That is implicit in my explanation. I am assuming that some policy is known and actions are selected. And this state value function is always denoted by the symbol V pi of S. Whichever papers of reinforcement learning you will read, uh, the community has been incredibly consistent with all these notations, which makes paper reading somewhat easier in the field of RL. So whenever you see V pi of S, it means that we are calculating the value function for a particular state, which is the expected value of the return which the agent receives, starting with that state and following the policy thereafter till the end of the episode. So this policy is denoted by pi. And the formula is something we have already seen before. It's the expected value of G of t, where G is the expected return, or G is simply the return. And remember how we calculate G? We don't just do R1 plus R2 plus R3, but we do R1 plus gamma times R2 plus gamma square times R3 plus dot dot dot. So here gamma is the discount factor. And we do this because immediate rewards are more valuable compared to rewards which are received later in the trajectory of the agent. So mathematically, this is expressed like this. It's okay if some of you are completely uncomfortable with this sigma notation. This is called as a sigma notation, where you have an index running from 0 to infinity. Essentially, what you are doing is that You're summing up all the rewards which the agent receives from one state till the end of the episode. And I can't emphasize the importance of this formula and the way we are defining value function, because it appears so many times, even in the definition of the most modern reinforcement learning algorithms like PPO and GRPO. The value function plays a crucial role because the final policy, which is this, for this policy, we need to estimate the value function. And that's why defining it properly is extremely important. Now we come to another definition, which is called as the action value function. So let's try to understand that in detail. So let's say you are at a specific state S, and from this state S, there are four possible actions. You can either take A1, you can take A2, you can take action A3, or you can take action A4. So there are four possible actions starting out from that single state S. And then all these four actions will have some different trajectories till the end of the episode. So this I will mark as end of the episode. Now we already know what the value of a state is. The value of this state is, you look at all these actions and you sum up all the possible trajectories which the agent takes in the entire summation of experiences, and you take a mean of that. That is the value. But you might ask me that, can we calculate values for specific trajectories? For example, what is the value of this trajectory? So what's the value if the agent is in a state S and takes action A1? What's the value if the agent is in a state and takes action A2? What's the value if the agent is a state in state S and takes action A3 and A4? All these four cases are going to have different values because the rewards which the agent receives in all these trajectories is going to be completely different. So this is called as the action value function, which is denoted by Q of S comma A. So this is also exactly the same, where we add up all the rewards. Let's say RT plus 1 plus gamma times RT plus 2 plus dot dot dot. The only difference from this value function is that here we are defining an action also. Again, this symbol Q is something which you will see repeated in literature so many times. And it's one of the most famous symbols in the reinforcement learning literature. So I want all of you to be comfortable with this Q symbol as we move along. So this is called as the action value function. It is formally defined as the expected return starting in a state, taking an action, and then following a policy thereafter. So one question some of you might be having is, how are these two related? So a simple way to understand this is, if you, let's say, we consider this example itself. If you do Q of S comma A1, if you do Q of S comma A2, Q of S comma A3, and Q of S comma A4, uh, there are four possible Q values, right? Now, it all depends on what policy your model or your agent has taken. If your agent has taken a policy which chooses A1, then Q of S comma A1 will exactly match V of S. If your agent has taken a policy which chooses action A2, then Q of S comma A2 will exactly match V of S, etc. So there is no predefined relation between Q of S comma A and V of S as such. It depends on the policy which the agent is choosing. So I would say that at the start of this lecture, these two definitions that we are defining, One is the state value function denoted by V of S, and second is the action value function, which is denoted by Q of S comma A. And again, the mathematical formula remains exactly the same as value function. The only difference is that we are calculating the expected value of the returns given the state and the action also. Okay, now we are going to take a step ahead and move closer towards our understanding of how do we find this policy. Now that we have defined, okay, what is a value function, what is a state value function, what is an action value function, let's take a step ahead and ask the question that how can we estimate the values of all the states? And we are going to look at this question in detail. This is called as the estimation or the prediction problem, where given an environment, given an agent, we want to estimate what is the value function. So our task is to estimate V of S. Now, to help you develop an intuition about this explanation, uh, before around 1950s, 60s, people really struggled to estimate V of S. And the reason they struggled is that how can you predict something which is received much later in the future? So unlike rewards, value is calculated by adding all the rewards which the agent receives in the future, right? So how can you estimate the value if it's difficult for you to look in the future? So this is why the planning type of problems were considered to be very challenging in the reinforcement learning community. But then all of it changed when a person called Richard Bellman, he made a very simple but very strong finding. And I'll refer to my other notes to explain this to you because I want to make sure this intuition is clear. I hope you're seeing my screen here now. This is the scientist. His name is Richard Bellman. And what he basically said is the value of being in a state is the expected reward for acting according to the policy plus the expected value of wherever you end up next. So let me explain that again through an example. Let's say you're playing the Pac-Man game and your objective is to move this Pac-Man left, right, up and down. So at every state, there are 4 possible actions and your goal is to collect as many pellets as possible. So the routine that you follow is if a ghost is nearby, you always move away. If there is a pellet, then you always move towards it and you never chase a fruit. So this is our policy. The policy is already given to us. We know how the agent is going to be moving inside the environment. Now we want to estimate the values of each of the state. So what we say is that uh, we want to find out if I start in any specific maze location with a policy, how many points will I score on average? That's the value for each state for this particular game of Pac-Man. So what the Bellman equation says is that the value of a state is given by the expected reward which you receive right now. So let's say I choose an action of going right and I grab a pellet. So I receive a reward of plus 10. So I add this reward to the expected value of the next state. So basically what we are saying is, let's say you are in this state S and from this state S, you take an action and you go to the state S dash and you receive a reward, which is R in this transition. So if let's say this is the diagram, now what Bellman equation said that value of this state is equal to whatever reward I receive from transitioning from state S to state S dash plus the value of the next state. And this might seem a bit too simplistic, or you might say that, okay, this seems like a recursive relation. On the left hand side, also you have a value, and on the right hand side, also you have a value. So, what exactly is the point of this? I'll show you in a moment how this is useful, but for now, I want you to just appreciate the simplicity of this equation. And this equation is again going to be at the center of the algorithm which helped us to create RL agents that played video games. Complex applications, right? But still at the heart of it is the Bellman equation, which states that the value of one state is equal to the expected or the immediate reward of transitioning to the next state plus the value of the next state. Let's take an example to understand this. So let's take this example, okay? In this example, what's happening is that we have two states A and B. So the agent from state A, the agent can only go to state B. And the reward the agent receives is +1 in the process. And if the agent is in state B, then the agent can only go back to state B again with a reward of +2. So now how would the Bellman equations look like in this process? So we use a discount factor of gamma. So in reality, I have given you a simplified version of this, but in reality, there is a gamma here which is added. So let's look at this example again. Okay, so now you want to find the value of, let's say, value of this state B. So let's use this formula. Value of the state B is equal to the immediate reward plus gamma times what is the next state here. From B, I am again going back to B. So plus gamma times value of B. And what is the reward is +2. So I'm going to write this equation as VB is equal to 2 plus 0.9 times VB. You can see this allows me to estimate VB. I can now say that VB is equal to 20. Now we'll write down the Bellman equation for the first state, which is the state A. Remember, from state A, you are going to state B. So VA is equal to the reward that you receive along the way, which is +1 plus 0.9 into the value of B, which is equal to 20 here, right? So if you multiply this, you get 1 plus 20 into 0.9, which is 1 plus 18, which is 90. So we have calculated the values of state A and we have calculated the value of state B by using this simple formula. Okay, so this is the Bellman equation, and we are going to look at a practical example soon. So don't worry if you don't completely understand this right now. Okay, so now what we are going to look at is, okay, we have figured out some method of estimating the value function, and we have figured out how to write an expression to estimate the value function of a state in terms of the value function of the next state. That's all we have figured out yet. We haven't yet seen how to solve for the value function. Now, what we want to do is, where do we finally want to? Yes, so Animesh has asked, why does the Bellman equation work? I'll explain. I'll come to it in a minute. I'll tell you our final objective, and we are going to go from the Bellman equation to the final objective. Our final objective is that, let's say this is a state S. At this state, I have four possible actions. I have no clue which action to take. And every action I take will land me in a different state. So now this action will land me here, this action will land me here. Then again here I'll have four possibilities. Here again I'll have four possibilities. So I want to make a leap from the Bellman equation to a stage where I want to confidently say that when you are in this state, only take this action, which is the action of going to the right. Then when you move to the next state, only take this action. I want to be able to tell that with a lot of confidence. That's exactly what I want. And we are going to make a jump in this lecture where we are going to cross this bridge together. We are going to understand how we can go from this recursive Bellman equation and exactly see how it works. So let us.
Okay, I found this on the web for this recursive Bellman.
Okay, so let's try to understand how exactly this leap is made, and how can we estimate the actions or predict the actions for every state which are accurate. So this brings us to something called as the Bellman optimality equation. So in the Bellman optimality equation, what we are going to do is we are going to look at the reward plus gamma times next state value. So let's say you are in this state S, and there are four possible actions from this state. We are going to look at the same example which I looked at before, A1, A2, A3, and A4. And we don't know what is the right action to take at this step. Now, what if this value function was available to us? So basically what we are saying is R plus gamma times V of S dash. This is what we want to evaluate, which is the value function of this state. Now, if there are four actions, then all these four actions will lead me down four different paths. So value function of the state S1 is going to be R1 plus gamma times, or we'll just call this state S, R1 plus gamma times value function of state S1, or it can be R2 plus gamma times value function of state S2, or it can be R3 plus gamma times value function of state S3, or it can be R4 plus gamma times value function of state S4. And these four are because of the four different actions. Now, what I will say is that there are four possible actions, right? Either I can take this, this, or this, but I will choose the action which gives me the maximum value of this combination, the addition of the immediate reward plus the discounted value of the next state. So essentially what I will do is I will take maximum of R plus gamma times V of S dash over all the possible actions, and I will take the action, I will choose the action which gives me, which has the maximum of both of these. This is how I'm going to choose actions for every state. So let me repeat this again because this really forms the central piece of the policies, the algorithms which we are going to discuss henceforth. Imagine that we are an agent and we are stuck in a state. We don't know where to go. There are four possible actions from that state. Now, to choose the best possible action, you calculate the value of the state for all the actions which I'll be choosing, and then you pick the action which gives you the best value. And how do you pick the best action? You calculate this expression and you take the maximum of that. You can also think of it as calculating the maximum of q of s comma a1, q of s comma a2, q of s comma a3, and q of s comma a4, where q is the action value function. So we are going to calculate the maximum of these four. And this is how we are going to pick our actions. And we are going to tell our agent that whenever you are encountering a state, you take your actions by looking at the q values for all the actions and picking the action which has the maximum q value. So this is what we want. Now the natural question all of you might ask is, this is fine, but how can we estimate this also? We do not know the estimate of the next state. So isn't this a recursive function? So how can we compare? Because on the left hand side, there is an unknown, which is the value function. There is an unknown on the right hand side also. So we cannot really compare these four expressions because we do not know the value function itself. Now, this is where the idea of dynamic programming really comes into the picture. So in dynamic programming, we'll do something very simple. So now, what I have told all of you right now is we are going to follow this. We are going to r plus gamma times v of s dash. Okay. Now, what we are going to do is we are going to use the concept of dynamic programming to iteratively update our estimations of the value function. So first, what I will say is the first step is initialize the value of all states to be 0. Okay, so what I say is that first, in the first iteration, we'll initialize the value of all states to be 0 and we will call this as v0 of s. This is an extremely bad initialization, I know, but we are going to improve it slowly. Now, what will be the next iteration? What we'll say is we will modify this equation by saying that v of k plus 1 of s is equal to maximum of for all the actions r plus gamma times v of k of s dash. Okay, so k plus 1 is the next iteration and k is the previous iteration. So let's see what we get from the beginning. First thing what we get is substitute k equal to 0 here. So you get v1 of s is equal to maximum of r plus gamma times v0 of s dash. But you know v0 of s dash. So now you can actually evaluate this expression and you can calculate v1. Right? Because you know the rewards that you are going to get in all the different actions. You just pick the action which gives the maximum of this expression. Now we again do the same thing for the second time. We do this where we say that v2 of s. Now we substitute k equal to 1 and we do v2 of s is equal to maximum of r plus gamma times v1 of s dash. And we take a maximum over all the actions. So imagine what we are doing here. Let's say there are 100 states in the environment. We are initializing the value of all the states to be 0. Okay. So I just want to I want you to close your eyes and imagine this for a moment. Just close your eyes and imagine that there are 100 balls in a field, which are the states. And I'm initially giving the values of 0 to all these 100 balls. Okay. So we are imagining a playground, let's say a football ground. There are 100 footballs, and all these footballs have a value of 0. Now, what I'm going to do is that I'm going to go to one football, and I'm going to look at what is the next state from this football. So let's say I look at the football which is directly in front, which is the next state. So I'm going to update the value of this football by looking at the previous value of the next football or the football in front. And I'm going to do this for all the footballs in the field. So what this will do is that initially I had given the value of 0 to all the footballs. Now what I'm doing is I am updating the values of all these footballs by using the previous values of the neighboring footballs from each football. So to make this even more clear, let's say you have 4 footballs here, which are the 4 states. Okay. Now, initially, all of these have a value of 0. Now, let's say from this state, the agent can either go to this or this football. Now, what I will do is I will do R1 plus gamma. This is R1, this is R2. Gamma times 0 because that was the initial value, and R2 plus gamma times 0. So I'll take the maximum of this and I will change the value of this football to either R1 or R2 depending on who is greater. And similarly, I will do this for all the footballs in the field, and I will keep on doing this till the time my value function converges. So typically what you will see is you will start with 0, you will do some additions, and after some time the value function will start to converge. This is exactly how the Bellman equation is going to be used in practice, and that is why this equation is so popular. Initially, when you look at it, it looks like this is just a recursive relation. Why is this so popular? It is so popular because by applying the method of dynamic programming to this recursive relation, you can actually solve for every state. You can solve for the value function, which is the optimal value function for that state. So now, after you iteratively solve these equations, whatever value functions you get for each state, those are going to be the optimal value functions. Okay, so this is why the method of dynamic programming became popular. It was the first methods or the first algorithm which was proposed to solve the reinforcement learning problem in the first place. But now you might have a question that uh, okay, this is fine, but is there a way to write down this algorithm in a way that it makes more intuitive sense? Okay, so what people do is to solve the dynamic programming problem, people perform 2 steps. The first step is called as policy, either prediction or control. Let me just check it. Okay, so the first step is called as, just a second. Okay, the first step is called as policy evaluation. So what does policy evaluation mean? Let's try to understand. So The first step is called as policy evaluation. So in policy evaluation, what happens is we assume a given policy. Let's say the policy is given to us, which is the policy called pi. It might be a very, very bad policy. It's fine, but this policy is given to us. Now, what we do is we use this equation. V of s is equal to r plus gamma v of s dash. Remember, there is no maximum here because the policy is already given to us. So we know what actions to take for every state. Okay. So we modify this by putting a k plus 1 here and putting a k here. And we solve this for 100, 200, 500, 1000 time steps until we get v pi of s. That means that until we are satisfied that, okay, this is the prediction of the value function for each of the state. This is called as the policy evaluation problem. Now you might say that this is fine, but this policy is not good. We just chose a random policy. So the second method or the second step in this process is called as policy improvement. And this is where it gets interesting. So in policy improvement, what happens is, let's say we are in this state. Okay, and there are 4 possible actions in this state. A1, A2, A3, and A4. And the Q values, which is the expected return, starting from that state, taking that action and following the policy thereafter is 30, 20, 40, and 50. Now, your value function this value function, when used for this state, is giving a value of 20. What does this mean? This means that you are choosing the action A2. Your policy is defined in such a way that for this state you are choosing a action of A2 because that's why you have got the value of 20. But is this the best possible action you can take for this state? No, right? Because you can see that this action is leading to a higher Q value. So it probably makes more sense to take this action for this state. So then what do is you modify that policy even further by saying that check all the states and check the Q values of all the actions for all the states. If the Q values or if the value function, whatever estimate the value function is giving us for all the states, if it matches the maximum Q value, then it's fine, no problem. But if there is a Q value for an action which is more than the value function for that state, then change the policy such that you select an action which maximizes the Q value. And this is how the policy is improved. So the diagram for policy improvement, it looks like this. Policy iteration, that first you choose a random policy, pi 0. You predict the value function for that random policy. Then you change your policy from pi 0 to pi 1 by looking at the Q values for all the states and making sure that the action that you choose for all the states, it matches the action which has the maximum Q value for that state. Then again you calculate the value function for the improved policy. Okay, then you again improve the policy. You keep on improving until you find that for all the states in my environment, the value function exactly matches the maximum Q value for all the states. This means that our policy is truly optimal, and this is the best policy which my agent can follow in this environment. This is how dynamic programming problems are solved in practice. So the first step is policy evaluation, and the second step is policy improvement. And both these steps happen one after the other continuously. It's like a process. First you estimate the value, then you improve the policy, again estimate the value, again improve the policy, and you continue to do that forever. So what we'll do is we will look at one example through which we will try to understand how is dynamic programming exactly used to calculate the optimal policy. So let's understand this through this example. So we'll be taking the example of a recycling robot, and we will be using the first method that we talked about, where we use the maximum equation, this equation, where we chose the maximum of all the actions for each state. So now first, let's try to understand the problem. In the recycling robot problem, the robot can be in one of the two states. Either the robot can have battery level which is high, or the robot can have battery level which is low. So there are two states for this reinforcement learning agent. And for each state, the robot has three options. Either the robot can continue searching, the robot can wait, or if the battery is completely discharged, the robot can go back to the charging station and recharge the battery. So first we'll look at a table which lists down all the possible states, the actions which are possible for that state, and the next state which the agent can move into. So from this example, you can see that first let's only focus on the first three columns, then I'll explain about the next two columns. If the current state is high and the action is searching, then the agent can either remain in high state or the state can become low. If the state of the agent is low and the agent is searching, then uh, either the agent will remain in the low state, or if the agent is moving to the high state, it probably means that the battery has discharged and you have to recharge the robot again. So it has been given a very bad review, which is of -3. This is something we don't want at all. We don't want the robot's battery to be depleted completely, and that's been given a negative reward. If you are in a low state, you can either wait so that you remain low. If you're in a high state, you can wait, you remain high. Another option in the low state is you recharge and then you become high. But for that, you get a zero reward. You don't get a penalty because you're not completely discharged. So this is the current state, the possible action to be taken from that state, and the next state which the agent can encounter after taking that action from the current state. Now in this column, I have written the probability of transitioning from state S to state S dash. So you can see many of these have a probability of 1. For example, if I am in a high state and I wait, then obviously my next state is going to be high. So the probability is 1. Or if I am in a low state and I recharge, then obviously my next state is going to be high. So the probability is 1. But here the probabilities are alpha and 1 minus alpha and beta and 1 minus beta. Because while searching, the state can remain high, or if the searching has happened for a long time, the state can become low as well. Now, what we are going to do is we are going to understand for both of these states, low and high, what is the action the agent should take out of the three possible actions. And this means that we want to understand the policy which our agent should follow. Right now, you can see from this table, I have three possible actions for each state, but I am completely confused. I don't know which action to take. And this is where the method of dynamic programming comes very handy to us. We'll try to understand how that can be used. So if I'm in a high state, I can either search or I can wait. If I search, I can either go to high or low. If I wait, I can either go to high or low. So this probability is actually zero. If you are in a high and you wait, then you can never become low. So we need not consider this path. So this is called as a backup diagram. It is a diagram which is very useful for writing down the dynamic programming equations, which are also called as the Bellman optimality equations in this case. So now here what we'll be doing is, first let's just consider this path. Okay, so in this path, there are two possible subpaths. So the value of this action is going to be, first is the probability of taking this path which goes from this middle state to the high state, which is alpha. Alpha times, you remember that equation r plus gamma of value of next state. That is exactly what we are doing here. R, which is this, the reward received from by going from this high state to the high state, R of search comma H, plus gamma times the value of this state. And another path you can take is this, where it goes to the low state from high state. The probability of that is 1 minus alpha. So you multiply that at the start, and the middle expression remains exactly the same. You do R search comma L, which is the reward received in this path, plus gamma times the value of this state, which is the low state. So this is the term one. And now here we have written uh, the value of this path if we are taking the search path. But there is a second path, which is the wait path also, right? And this actually looks very similar to the expression which we wrote, which is the reward received plus gamma times value of the next state, which is the high state here. You can see here, if I wait, I can never go to low. So I'm just in the high state. Now there are two terms, right? Because of two possible actions. But remember in the previous discussion, we had taken the maximum of these two terms. So that is exactly what is done here. If term 1 is greater than term 2, the robot will search. If term 2 is greater than term 1, then the robot will wait. So we take a maximum of these two terms as the value function of the high state. And similarly, we can calculate the value function of the low state, in which we get three equations instead of two, because we have three possible actions, which is search, wait, or recharge. So we have to take the best of these three possible actions. So we have term 1, term 2, term 3, and we'll take the maximum of these three terms. So now you can see that we have 5 equations in total. And we have to solve these equations to find out the value function, the optimal value function of both the states, the low state and the high state, which will help us to choose which among these two terms is greater. If this is the greater term, we'll say that when you are in a high state, only choose to search, or when you are in low state, then only choose to wait. Something like that. That will inform our policy. So this is how practical problems like this recycling robot is solved using Bellman optimality equations. But here again, you can see there is a value function which is coming on the right hand side also. And here we are not exactly using those iterative style of equations where we had V0, V1, V2, V3. But in Bellman optimality equations, there is a different approach. You directly take the maximum. So You avoid going through all those iterations. But even this is not very easy to solve. And the reason why this is not easy to solve is, if you have 100 states in an equation or in an environment, then you will get equations which are more than 100. And you will have to solve all those equations simultaneously to predict the value of all the states. And that is the reason dynamic programming is a method which currently no one uses in practice. And the reason people don't use it in practice is because of two things. So let me come to the notes again. So the reason people don't use it in practice is because dynamic programming methods require a complete model of the environment. Remember, in the recycling robot example, we had the transition probabilities from S to S dash, and we had written the transition probabilities in the format of a table. Now, all that information is not available to us a priori. If you are making an agent and you are teaching the agent to play the game of chess, how can you ever know the information of what is the probability of transitioning from this configuration of chess pieces to that configuration of chess pieces? So that is something which is very hard to acquire. And dynamic programming methods require a complete model of the environment. This is impossible to obtain in most of the cases. Shishir has asked a question. I'll come to this question towards the end of today's lecture regarding continuous and discrete values. But right now, I want to discuss other form of methods which are called as Monte Carlo methods. These are methods which basically do not require a model of the environment, but they only learn through experience. So Monte Carlo methods are considered to be very useful compared to dynamic programming because of this sole reason. So let's take a simple example. Let's say this is our environment, and we are here. We are this small yellow dot, which is on the top left of the screen over here. And our goal is to somehow take a path which avoids the obstacles and reaches the goal in the least amount of steps. So there are two approaches we can take for this problem. The first approach that we can take is we can use the dynamic programming method. And the dynamic programming methods would require you to know the probability of transition from each state S to the next state S dash. And all the states would be updated simultaneously at once. So here you can see there are how many states? Around 5 into 5. There are slightly less because some are obstacles. So there are 20 to 25 states. So you will have 25 equations in 25 unknowns. But at the same time, you don't know the probability of these transitions. If you know the probabilities, that's great. For example, if you say that for every state, I'm going to take the actions of left, right, up and down with equal probabilities, then you know the probability. But in majority of the cases, you won't know the probability of transitioning from state. So this is not a practical method. So I'm going to put a cross in front of it. Now in Monte Carlo method, what is done is you randomly start simulating episodes in the environment. So let's say my first episode is this. I go here, I go here, 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 and here. Okay, so what I do is I go to all these states, and let's say these states are numbered as 1, 1, 2, 3, 4, 5, and 6. So now what you do is, let's look at state 1. We can calculate the return obtained. So G of 1 uh, at state 1. This is the first return, which is equal to, this is, let's say, R1, R2, R3, R4, R5, R6. So this is equal to R1 plus R2 plus dot 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 plus R6. So this is the addition of all the returns which the agent receives from starting from this state till the end of the episode. Similarly, we do this for S2, S3, S4, S5, and S6. Okay. Then what we do is we simulate another episode. Now, this episode can be completely different from the previous episode. Let's say it's something like this. Now, what I do is I again look at this state. From this time, I calculate the second reward, which is G of 2 of S1. And again, R1, R2, R3, R4, R5. I do a summation of all of this. Now you can see I have two estimates of the returns for the same state. So I'll take the average of all those estimates. And this is exactly how the value functions of the states are calculated in Monte Carlo method. It is pretty simple to understand compared to dynamic programming. Essentially, what you do is you simulate a large number of episodes, and you calculate the returns for all the states in those episodes, and you take the average of them. For example, now after episode 2, I will update the value function of state S1 as G1 plus G2 by 2. And after 100 episodes, it will be G1 plus dot 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 plus G100 divided by 100. So my value function will become better and better and better. And this is very useful compared to dynamic programming because you don't need any model of the environment for this. I have no clue how the environment behaves. I just let my agent free, do whatever you want to do. I'm just going to collect the rewards and then average all the rewards and improve my predictions. So here the only thing required is to simulate as much episodes as possible. One thing you might ask is, what if certain paths are never chosen in the simulations? What if this path is never chosen, for example, in the simulation? So we are going to look at how these things are taken care of, but at the heart of it, this is what Monte Carlo methods do. They simulate a bunch of trajectories, episodes, and calculate the average of all the states for all these different trajectories and update the value functions iteratively. So this is called as the Monte Carlo prediction problem. And what we do here is we initialize an empty list of returns, generate an episode, and for each state in the episode, calculate the return, append the return to the returns list, and take the average of all of it. We are going to look at a very good example of this practical example today, so you will understand how this is done. Don't worry about it. Okay, now one last thing to discuss in the Monte Carlo method is when taking actions in the Monte Carlo, uh, how the actions currently are chosen is, yes, so the same question Shravan has also asked. In the Monte Carlo methods, we have now just learned to predict the value functions, right? The question that you might ask is, how are the actions chosen in Monte Carlo? So this is Monte Carlo prediction, what we looked at. How do we take actions in Monte Carlo methods? So usually what is done is, currently I showed you how the state value functions, which is V of S, that is updated. Now exact same procedure is used to calculate Q of S comma A. Okay, so when I say exact same procedure, I mean that uh, you simulate a bunch of episodes and you look at one state and an action taken from that state. For example, in this example, instead of calling G2 of S comma 1, we'll say G1 of S1 comma right, which is the right action. Okay, and here we'll say G2 of S1 comma right action, and we'll say Q of S1 comma right is equal to G1 plus G2 by 2. Exact same process, but instead of calculating value functions, we calculate the action value functions instead of calculating the state value functions. And why is this done? Because The action value functions allow us to directly choose actions for each state. Let's say we are evaluating the actions for one state S. So these are all the actions and these are the Q values, Q of S comma A. So let's say there are two, A1 and A2, and these values are 30 and 50. So our policy is that we are going to choose whichever action has the maximum Q value. So this is how Monte Carlo method is used to dictate or form the policy of our agent. Now you can see how we are bridging the gap between simulating environments or moving through an environment and finding an optimal policy. We are simulating that by estimating the action value functions and then using the action value functions to pick actions. Now, with respect to the question which is asked in the chat, how are all states and actions explored? In reality, what is done is, as we had also covered in the first lecture, we do a balance between exploration and exploitation. So whatever I have discussed right now, uh, choosing the action which has the maximum Q value, that is called as exploitation because we are just looking at the Q values and choosing maximum. But exploration is where you pick a random action. So this policy is called as epsilon greedy policy, which means that out of 100 times, 90 times you will use exploitation and 10 times you will use exploration. So 10 times you will look at the Q table and you will forget about the magnitudes. You will take a random value or a random action from the Q table. And this is exactly how the Monte Carlo methods are implemented in practice. If you do not take these random actions, then what if some paths like these are never explored by the agent? This is a very realistic scenario and it can happen. This will never happen with dynamic programming because in dynamic programming, we are calculating the values of all the states in the environment. But here, since we are simulating episodes, we might miss some states. So we might not be able to understand whether maybe there was an optimal path which we did not even experience. And that is why the epsilon greedy policy is extremely useful in practice. So two things I want you to take away from this discussion. Firstly, when Monte Carlo method is used, we always use the action value functions, uh, action value function to estimate or to find out the actions. And secondly, we use an epsilon greedy policy. We don't use a greedy policy, but an epsilon greedy policy because we want to balance the exploration and exploitation very well. Now, after Monte Carlo method was discovered, people said that this is fine, but there is one major problem in this method. Some of you might have guessed it already. The problem is that I am updating my value function for each state only after the entire episode is completed, right? So these returns R1, R2, R3, R4, R5, only after I receive all the rewards and I reach till the end of the episode, I am updating the value function or the action value function for all the states and actions I'm seeing in that particular episode. But is this very efficient? Why do I need to wait till the end of the episode? Why don't I immediately update my value functions after each step I take in the environment? So imagine that you're learning to ride a bicycle, right? And you're going from a start line to a finish line. Do you update your knowledge of learning after you finish or go from start to end, or you update it incrementally? If you make a mistake, you know, okay, I don't want to make this. Let me go ahead and see what happens. So how humans think is that we think on an incremental basis. We make updates incrementally. We do not wait till the end of the episode to make updates. And this is exactly what people realize that, okay, this is something which needs to be improved. And this is where temporal difference methods were born. So temporal difference methods, they are quite similar to Monte Carlo in a way that they do learn from raw experience and they don't need a model of the environment. And they are similar to dynamic programming because we do not wait for the final outcome and we update estimates based on other learned estimates. So temporal difference methods were considered to be a best of both the worlds. You have one world of dynamic programming where you are updating your estimates based on other past estimates. And in Monte Carlo, you are updating your estimates based on the raw experience and you don't need any model of the environment. So let's see how exactly does uh, temporal difference methods. Let's see how they work, and we'll try to develop a very strong intuition for this with a very nice example. So what we'll do is we will see. Yeah, so in the temporal difference methods, let's first consider Monte Carlo method, and let's say that we have completed 100 episodes and we have collected 100 experiences, and using the Monte Carlo methods, now all of us know that the value function of a state can be written as the first return plus the second return plus the third return plus dot 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 the 99 or the 100 return divided by 100. This is how my value function is going to be updated after I generate 100 episodes of the agent interacting with the environment. Now, let's say we collect the 101st episode. So the value function will be updated like this. We just add one more entry and divide by 101. This can be expressed like this. So value function at the 101th episode is equal to value function of the 100th episode plus 1 divided by 101 into bracket the return received for the 101st episode minus the past estimate of the value function. Now this also can be written as new estimate is equal to old estimate plus alpha, which is the step size, return minus the old estimate. So what this equation tells you is that if the return is same as the old estimate, my new estimate will be same as the old estimate because this term will be 0. If the return is very far from the old estimate, it means that my new estimate will also be quite different from the old estimate. So this is something which is one of the most iconic equations because it's like a simple way to visualize or imagine how the Monte Carlo equation works. And you can actually understand why this equation makes sense because as we are collecting more trajectories and more episodes, if we get new information, we should update our value function as per and move it towards the new information. But if the information is same as the old information, then there is no reason to update the old information. So now, so here, this is why we have to wait till the end of the episode in Monte Carlo because you cannot calculate this return unless the entire episode is basically completed. Now in temporal difference methods, what people said is that why don't we replace this return by the immediate reward plus the value of the next state. So which means that if instead of waiting till the end of the episode, why don't we just uh, use the reward which I am getting by transitioning from one state to the next state and add it to the value function old estimate of the next state. So this looks something like this, where here you can see the return has been completely replaced by a new term which does not, we need to wait till the end of the episode to estimate this term. So this term basically says that the next update of the value function is the current value function for that state plus alpha times whatever reward I am receiving while transitioning from that state to the next state minus the current estimate of the value function for that state. And I'll come to one very interesting example where you will understand this. So let's take an example of us going from office to home, right? Um, and let's say we are somewhere on the left at junction number 1 and we want to reach to junction number 9. And in between there are different junctions named 2, 3, 4, 5, 6, 7, 8. So we want to go from the office to our home, and in between there are a lot of junctions. So we are interested to find how much time it takes from our office to our home by going through all these junctions. Now let us understand how we can solve this problem. So firstly, here the states are the junctions 1, 2, 3, 4, 5, 6, 7, 8, 9. And the rewards are the time taken between the junctions. Okay, so T0, T1, T2, T3, etc. Now, our goal is to finally estimate the values of each of this state. For example, the value of state 2 is going to be T1 plus T2 plus 3T, T4 dot dot dot. So that makes sense because that will be an indicative of how much time it's going to require for me to go from state 2 to home. Similarly, for state 6, the value is going to be T5 plus T6 plus T7, which is going to be indicative of how much time I require to go from this state to home. So our final goal is to calculate the values of all these states using both Monte Carlo and the temporal difference methods. So now let's look at the Monte Carlo method. So let's focus on junction number 3. So junction number 3, using the previous formula, what we know is value function of junction 3, the new estimate, is equal to the old estimate of value function of junction 3 plus alpha times the return. Now, what is the return? T2 plus T3 plus T4, T5, T6, T7, which means that imagine you are driving a car and you are at junction 3 and your current estimate shows that the value function is 100 minutes. So it takes 100 minutes to go from 3 to 9. But to make the next update, you need to go all the way from this state to home, and then only you can calculate the return. In other words, let's say if there is a traffic jam from 3 to 4, I know that now it's going to take more than 100 minutes for me to reach because of this jam. But I cannot update my value function immediately unless I reach home because I want to do T2 plus T3 plus T7, etc. So this T6, T7 are obtained only in the end of the episode, right? This is one of the major drawbacks of Monte Carlo methods. Now, when temporal difference methods came, they came and said that, okay, don't worry about what's coming later. If you see there is a jam here, immediately update your value function by this formula, which says the new estimate is equal to the old estimate plus alpha times, look at this term in the middle. This is how we are approximating the return. We are calculating the immediate reward. This is where the jam happens. T2 is high. Value of T2 will be high in jam. Plus alpha times the value of the state 4, which is the value of this state, which will be whatever it was in the previous estimate. So T2 plus gamma times V4 is an approximation to the return which we receive from this state. And if you see closely, this is also a consequence of the Bellman equation. because the Bellman equation told us that the value of a state is equal to the immediate return plus the value of the next state. So why don't we use that here when estimating the return? And this is exactly how temporal difference can help us immediately take into account the information of the jam. So you can see if the previous value of 100 minutes, it will be 100 plus alpha times whatever this jam is, 5 minutes. And the value of that state will be immediately increased by some small amount. We don't want to increase it by a big amount. That's why we have an alpha over here. But it slightly nudges it towards the jam value. So it's going to be 100 plus maybe some 2.5, 2.6 or something like that. This is the main difference between Monte Carlo methods and temporal difference methods. And this is why temporal difference methods are considered to be extremely useful in practice, because they are very efficient in terms of updates. You don't need to wait till the end of the episode to do updates. Now, when we look at temporal difference methods, there are two types of algorithms or two names of algorithms. The first algorithm is called as SARSA. And this is the exact same formula which we discussed before. The value of a state is equal to old value plus alpha times reward plus gamma times the next value minus the old value. Now, why is this algorithm called SARSA? Is because if you just convert this value function to the state value functions, you can see that you have S, A, R, S dash and A dash. So you have all these variables, right? And if you see them together, you see a word forming, SARSA. So this is where this algorithm SARSA comes from. It is a temporal difference algorithm to uh, update the action values in such a way that they become better and better and better, so that we can take better actions when we encounter every state. So whenever I discuss any method, you might have noticed that I first discuss about the intuition behind that method, the formula, and then I immediately go to the action values. The reason I go to the action values is because to implement an agent in practice, value of a state is not very useful, but value of states and actions is very useful, because it's a very direct information. I can directly look at the queue table and I can see that for every state, which is the best possible action. Okay, let me go ahead and pick that action for each state. Now there is another algorithm which people used, which proved to be even better than SARSA. And this had only a small difference from SARSA, which is called as queue learning. So it was developed by this person, Chris Watkins, in 1992. It is considered to be one of the most fundamental papers in the field of machine learning. And actually, this was at the heart of the paper in 2013, where DeepMind used Q learning to play Atari games. And Q learning is very, very similar to SARSA. The only difference is that uh, they use a maximum here instead of just Q of S dash comma A dash. So what Q learning says is that the new estimate of the action value is equal to the old estimate plus alpha times the immediate reward plus gamma times you pick an action which gives me the maximum value of uh, the Q value for the next state, and then subtract it from Q. In SARSA, we just had Q of S dash comma A dash. We did not have a maximum here. So this is one of the main fundamental difference than SARSA. And some of you might ask why is that so different? Aren't in SARSA we are calculating, finally we are looking at the Q table and we are calculating the actions which give the maximum Q value, right? Well, that's kind of correct, but let's look at the SARSA algorithm more in detail. In SARSA, what we do is we initialize the states uh, and then we choose for every state, we choose actions using the epsilon greedy policy. So let's say our initial estimate of Q values is very bad, but we still choose actions using the epsilon greedy policy. And then after each action, we observe the reward and the next state. Again, choose the next action using epsilon greedy policy and then calculate this update using the Sarsa equation. Now here there is no maximum of actions performed because we are using an epsilon greedy policy. But in Q learning, what you are saying is that here we are not using an epsilon greedy policy here, but we are using a greedy policy. So we are behaving according to the epsilon greedy policy, and in the actual algorithm, we are using a greedy policy. That's why it is called as off policy learning. So Q learning is an example of an off policy learning algorithm. Okay, so today's lecture has been very theory heavy, and I'm personally aware of it, but it is very important for all of you to understand, and I could not avoid covering this theory, even though how hard I thought about it. It was very important to cover. Now, what we will do is we will revise our concepts of Monte Carlo and temporal difference by looking at a very practical example. And you remember the lunar lander which we simulated? Now we are going to update that lunar lander code by using Monte Carlo and temporal difference methods. So before I go to the actual coding, I want to actually code in front of you the major aspects of uh, just a second. The code aspects of Monte Carlo and temporal difference methods. So let me just open up a new folder and try to see. Yeah. So there was a folder I had created called RL Bootcamp Visuara. So let me open up a new window. So you can also open up VS Code or any code editor which you use on the side. And we are going to write down the basic algorithms for Monte Carlo and temporal difference, which will be used in our final codes. So this was the last example which we had written. Now what we are going to do is that going to go here and we are going to just look at algorithms. So first we are going to look at Monte Carlo code. Okay, so in both Monte Carlo and temporal difference, an important thing is to choose the right action. So I'm going to zoom in a little bit here. Okay, so choose actions. So as I explained, the actions are chosen using the epsilon greedy method. But what does an epsilon greedy method actually mean? Let's look at it. Okay, so we start by defining a function, define choose action. And we pass two parameters here. We pass a state and we pass an epsilon. Okay. Then what we do is if np dot random dot rand is less than epsilon, so this means that we randomly select a seed from 0 and 1, and if it's less than epsilon, we return a random action. So np dot random dot rand int, and remember this environment dot action space. So this env dot action space dot n, this basically gives me the list of all possible actions. So in the lunar lander, we had 4 actions. So out of these 4 actions, it's going to choose a random action. That's what this line means. But if the number is greater than epsilon, we want to return np.argmax. So we want to return the maximum from the Q table. Okay, so we are going to return the action which gives me the maximum action value. So this is something I have been reiterating in this lecture, the importance of storing the Q values properly. And once the Q values is stored, you can see how our action defining the action becomes so straightforward. And by the way, this remains exactly the same for both Monte Carlo and temporal difference methods. Now let's look at the Monte Carlo main code, the core of Monte Carlo. Okay, so for P in range episode length -1. So you can see here we are going in the reverse direction. Let's say the episode length is 50. So here we are going from 49 to -1 and taking a step of -1. So we are going in reverse. I'll explain why that is the case. And we define G, which is the return, as gamma into G plus episode rewards. Now, this is something which is very interesting, and I want you to very clearly understand this. So let's say the initial value of G, by the way, is 0. We are going to initialize it as 0. Now, just imagine that you are going from a start of the episode to the end of the episode, okay? And here we are starting from the last step in the episode, okay? Now, whenever you are in the last state, there is no next state. So the return is always going to be, so this is going to be 0 because G is 0. So the return is going to match the reward received in the last state of the episode, which makes sense. Now, if it doesn't match, if you are in a state which is next to last, right? Which is, let's say we have 10 states where 10 is the last state. Let's say you are in the 9th state. Then this G is going to be gamma times reward in the last state plus reward going from state 49 to 50. Maybe it's better to explain this here. So let's say you have these two states, right? 49 and 50. Okay, now the return for, and we have a complete episode leading up from some particular, so there are 50 steps from step 0 to step 50. And this is the last step. So I am receiving some reward in this state, which is going to be the same as the return. But for state 49, what we want is, we want the return to be reward in this state R plus gamma times the reward received in the state 50. Similarly, if you go back even further in state 48, we want the reward to be R plus gamma times reward in state 49 plus gamma square time rewards in 50. This is exactly how we calculate the return for all the states. The only difference is that we are going backwards. That is why this formulation works well. Where is that? Yeah, that is why this formulation works well. And then what we are going to do is, from each episode, we are going to track the state episodes and we are going to track the action also. Okay, and then we are going to calculate the return sum. So for every state and action pair, why do we do this plus equal g? Why not just stay content with this g? The reason is that the same state and action might be encountered in multiple episodes. So you want to add up the returns for all the episodes and then take an average of that. So to take the average successfully, we need to first count how many times has that state and action be visited. So the count is incremented, and then the last step is easy. We just update the Q table. That's it. This is how our main core Monte Carlo code looks like. It's what we are doing is that we are calculating the return for each state and action, and then we are averaging it for all the episodes. Now, what I want to do is that I want to run a piece of code here, which is we are going to rename it as Monte Carlo.py, and I want you to copy those codes. So okay, so I'll be pasting one code in the chat right now. So Shishir has a good question. How do we select a value of gamma? I'll probably answer that towards the end of this lecture. So I'm posting a code over here, or maybe it's better to uh, share a file where the code is written. I think that will be easier to access for all of you. Okay, so have a look at this document. And basically here we have written the same piece of code as we looked at, which is the main code is written over here. This is the core. The rest of it is just in the first step, we have discretized the environment, the states and actions, because the lunar lander is an environment which has a continuous set of states, but we have to discretize it uh, because our algorithms do not work for continuous states. We have different algorithms for that, but don't worry about all these things. These things will become clear towards the end of the course, but right now I just want you to focus on this. The packages that will be needed for this are Gymnasium we have already installed, NumPy, Torch, TensorBoard, and MoviePy. So you can do pip install Gymnasium box2d in bracket, NumPy, Torch, and TensorBoard. So if you have not heard about TensorBoard before, I'll show it to you today. It's one of the best tools which is integrated in Python itself for visualizing our runs. So I use it for RL problems more often. So let's go ahead and run this. So you can see that at the bottom, total episodes to train are 30,000. And as the number of episodes go on increasing, you can see our rewards are also increasing with time. So minus 79, minus 53, minus 32, minus 23. It's good, right? So, which probably means that our agent is learning. It's not like we did at the end of first lecture where the agent was really taking some random actions, but here the agent is actually learning. And how is the agent learning? We are collecting a lot of experiences, we are collecting a lot of episodes, and we are updating our estimates of the Q values for each state and action after each episode. So our Q values are getting more accurate and more accurate, which is what is helping us select accurate actions. How are we selecting actions? We are using epsilon greedy policy. For every state, I am selecting an action which has the maximum Q value 90% of the times. But for a small percentage of the times, I'm choosing a very random action. And that's why you see sometimes the rewards actually fluctuate because it's not a very greedy policy I'm taking, but I want to explore the environment more. So I am taking a random policy. Now, Monte Carlo codes, here you can see that without the rewards are updating only after the end of the episode, right? So it's a bit slow generally, but I want you to not just run this code, but understand the theory behind it. Some parts of the codes I have deliberately not explained regarding discretization of space, etc. But the main core of the code I have explained to you how the algorithm actually works. And you can see the rewards are slowly increasing and uh, we'll be so there are two steps followed in this code. First is we have to train the agent for 30,000 steps and then we have to test it. Very similar to what we do in classical machine learning approaches where we have a training process and we have a testing process. But unlike machine learning where they have training data set and testing data set, here we do not have anything like that because the environment is the same for training and testing both. The only difference is that we simulate the environment for 30,000 steps during training, but testing is where we simulate only 3 or 4 or 5 times maximum. So slowly my rewards are increasing and let's see. If you are able to run this code, can you type yes in the chat so that I'll be aware that all of you are able to run it? Okay, great. Mayank is able to run the code and Monideepa also, Shishir. Okay, great. Regarding Shishir's question, Shishir, you explore this tool called Optuna. It is one of the best tools for hyperparameter tuning, which I generally use. And I have used it for RL problems also. But the way the values, so most of the times in standard practice, this value is not changed. But if you are working on some research projects where you want to plot the accuracy versus the discount factor. So here you can see there are two hyperparameters. One is the discount factor gamma, and second is alpha. Remember in our theoretical discussion on temporal difference and Monte Carlo, there was a step size parameter alpha. That is also an hyperparameter actually. So now the training is completed and it will start with the testing. So successful landings one. So successful landing I have defined by when it receives a score more than 200. It's a manual definition and test reward is 7.9. Now I'll explain the part which I enjoy the most, which is seeing the results in TensorBoard. You can see there is a runs folder created here. Let us visualize this. So let's see. So there is one command which I generally use, TensorBoard dash log, I think. Let's see. TensorBoard dash log and dash dash runs. Uh, TensorBoard, yeah. So this is the command I want you to execute. TensorBoard dash dash log dir equal to runs. I have pasted it in the chat right now. Now, when you type this, you will see there is one local host 6010 created over here. Just click on it and open it. So this is where our statistics will be given. So here there are three cards: training, testing, and final. So go to training and you can clearly see how the reward increases. So when I see a profile like this, I feel confident that, okay, my training has actually worked. You can see here the reward increases with time. And here I have used an epsilon decay strategy. So what I generally do, what people also do is that initially they choose a high epsilon because in the initial stages, exploration has to be more, but then in the final stages, epsilon has to be low because your model is already better. So there is no need of exploration that much. And then here you can see in the testing, the reward, it's a bit erratic because there are only three samples which I have tested. Now, why don't we go ahead and discuss about temporal difference methods? So again, as we did with Monte Carlo, till that time you can just focus on Monte Carlo right now. I'll just not here. Okay, and by the way, there are some videos generated here. So just run those videos and see if they are better than our first. Uh, Let me actually show you one of the videos which I have run. So in my experience, temporal difference videos are much longer, and the longer the videos, the better, because then we'll have, yeah. So here you can see hands-on RL learning Visuara, and here videos MC, which is Monte Carlo, and I'll run this video 73 KB. So it's like 10 seconds. So you can see it goes off and slowly settles down on the surface. I have had videos with uh, 12, 13 seconds also. So you might see different times, but there is certainly an improvement over what we did with a random agent, right? Now with temporal difference, it's actually very similar, but the main difference is in the main function. So what we do here is the action remains the same. So action function. So action is equal to choose action state comma epsilon. Now here we need to write down the next step. This is very important because remember in the Q learning algorithm, we had Q of S dash comma A dash. So next state, reward, done and truncated. And truncated is equal to env dot step action. If you remember in the first example, we had written this. I'll just show you. In example 2, we had written this env dot step and it accepted the action as an input. So exactly the same, when we give an action as an input, the OpenAI Gymnasium environment gives us the next state, it gives us the reward, it gives us a flag whether the episode is completed or not, and it gives us a flag whether the episode is truncated or not. This is usually, I've never used the truncated flag. And then what you do is you just discretize this state. This is not very important, but you will see it in the code. So that's why I'm writing it. Discretize. Next state. Now is the most important part. If the episode is not completed or not truncated, pay close action to the temporal difference target. Okay. So this target is actually exactly the same as our formula reward plus gamma times. Remember there was a maximum here, np dot max q of this one, next state discrete. So this is our target. Otherwise, if the episode is completed, you are in the last state. So The target is just the reward that you get. Now you update your queue table. This is done in both the cases, but here the update is done based on not on the returns but on the TD target, which is equal to alpha into TD target minus the previous state. In Monte Carlo, this TD target is replaced by the return. Here the TD target is replaced by this. So, and then you basically get the total reward, and then you set the next state. So you can see here we are updating the queue after at each step of the episode. Okay, so this is the basics of how the queue learning, and when you see the code, you will see this exact same procedure is implemented. I'll just delete this for now. Okay, so now we are going to run a code which is uh, regarding temporal difference learning methods, and I'm going to update the same document which I shared with all of you. So it's going to be updated here. Okay, so go ahead and run this. It won't require any additional modules. I'll also do that. Paste it. Let's look at. So I'm going to just cancel this one time because I've given 50,000 steps. It will take long time. Let's say I give the steps as 15,000 to start off with. You can keep it at 50,000. I would recommend that because we are going to compare both TD and Monte Carlo at the end of it. In my experience, temporal difference always works slightly better than Monte Carlo. As a homework problem, I want all of you to search about or research about this another version of Monte Carlo, which is called as Monte Carlo first visit. And in that version, what happens is that uh, if in an episode a state is encountered 2 or 3 times, we only consider the update for the first time the state is encountered. The other two updates are ignored, and people have seen that you can get a lot of improvements in the performance uh, if you use the first visit Monte Carlo algorithm. Okay, so this process might take some time. I'm just going to wait for some time. Till that time, I'll show you some videos which I got when I ran the Monte Carlo or the temporal difference simulations. So if you look at these videos, right, I got some videos which were this I got pretty long videos. You can see the agent stays there for some time here. This will never happen if you choose random actions because it's as if it's evaluating, and it's like a very deliberate motion. It doesn't look like a random motion. And all the episodes here are long. All the testing episodes you will see here also slowly comes down and gradually settles to the surface, which is quite cool, I think, because Okay, in the end, it orients itself, but using these classical algorithms, you can achieve this level of performance. So, this is what I call as the three horsemen of classical reinforcement learning: dynamic programming, Monte Carlo methods, and temporal difference methods. Each one kind of builds on top of the other. And here you can see the rewards are not that great, but they will increase if you increase more number of episodes. So let's go ahead to TensorFlow. To run it, it will be automatically saved. So you will see another link here, the tensor board, and you can basically compare both these side by side. So let's compare this. Yeah, here. So here it shows that my temporal difference method is actually slow to learn, but I have observed that it catches up after a few episodes and it performs better. So Pramod is asking that what does discretize do? What discretize does is, so here in the lunar landing example, we had 8 observations, right? So discretize, let's say you have a observation or a state which runs from 0 to 100 value. It can have any values in between. So I create bins. So let's say I create 5 bins. So here, this is a heavy level of discretization because I say that whenever something falls here, it will have a state of 0. Here it will have a state of observation 1, observation 2, observation 3, and observation 4. This is the meaning of discretization. We convert the continuous nature of a variable into discrete values. So this is what discretization does.